Hello.
Carly, I need to see your face. Uh, I've got to do some things to get ready. We doing okay? Do you have any questions?
Nope, I'm all good, just early.
Okay. Just trying to figure out. I thought I'd fix this the other day, and apparently I didn't. There we go. Okay. Any questions, Carly, Jeremiah?
I do actually have a question about the lab. So I did the full graph and everything. I had the correct data because you said that the slope would be negative, it would be descending, all that good stuff. But I had a question about how to obtain the slope line from two given points. Because we're only given the 2 points, but
Whoa! You're giving more points than that. You're talking about the L and a P versus the L and a P versus L and a P versus
I'm talking
one over
about
temperature.
Yeah, I did all those. I'm talking about the 2 points to form the slope from. Because part B,
did you do it Excel?
I did it Google Sheets and then transferred to Excel to see if there was a difference. They're both identical though, so it's more of a calculation issue.
Okay, my headphones are. Can you hear me, Jeremiah?
Yes.
Okay, my headphones are finally giving out.
That's never good.
No, especially I got a whole bunch of other ones, but they don't. There must be headphones must be different because the other headphones don't work in this.
Yeah, I decided to give up the wires.
Yeah, probably sure. But Jeremiah, you have more than 2 points.
It was, so I've got a total of 1, 2, 3, 4, 5, 6, 7, 8, 9 points on the graph.
Yeah.
But you're supposed to grab a high and a low point to form a slope that are not the data points.
Okay.
So I just grabbed 2 random values from.
But wait a second, Jeremiah, did you do it on Excel?
Yes.
Then just print out the equation of the line.
Yeah, that's what I did. Every time that I try to plug it into the values, though, they become excessively high.
I'm talking 4,000 or so.
My slope came out to like negative 2,200, somewhere around there.
That's fine.
Okay.
Yeah, it's going to be that high. It's going to be that high, Jeremiah, because what you're going to do is you're then multiplying that by R, correct?
Right.
Okay, so you multiply that by 8, that gets you in the 100,000 or at least the tens of thousands.
Oh, right? Gotcha. So we only needed this one slope. So that's what that was. Okay.
Yes. And basically, when you get to that point, you have to, because you're multiplying by R, which is in joules, and heat of vaporization is in kilojoules, that big large number is going to get divided by 1,000.
Gotcha.
Okay.
Okay. Gotcha. Yeah, I got confused because it was like graph all of this and then use 2 random points to form a slope. So I was trying to form a slope.
They're assuming that I'm not letting you use Excel.
Gotcha.
All right. Okay. So that's all that's about.
That makes more sense.
Carly, Marin, do you have anything?
No, I was just logging on to see if I had any problems logging on or not.
Yeah, I logged on because I needed to go. I got a new toy. See, I can draw things. Ooh. Except I don't know how to erase.
Maybe holding down right click.
I can undo all this, but that's a pain in the ass. I need to be able to do the whole thing. Oh, how about clear?
Oh, that works.
Yay, okay. I can read. Amazing. Nobody was hurt by the hurricane, were they?
Nah, it filled up the pond.
Marin or Carly, neither one hurt by the hurricane?
Nope. And I live on the water, so works out pretty well.
You live on the water?
Yeah.
Where
So
at?
basically in Zone A, in St. Pete, like near Madeira Beach.
Okay.
Yeah.
I live 2 blocks away, but I'm not in Zone A, if you can believe that. I'm high enough. It gets that high that I'm like in a C. But
Awesome.
if you've ever been around South 22nd Ave, Chataway, that's my neighborhood.
Gotcha.
So actually it was nothing. I was sitting here hoping for something to happen. Knocked out a few of these crazy branches that we have around here, but I got nothing. Not like the morning my wife woke me up after about Irma. She woke me up and said, hey, we got a category 4 headed straight for us in an hour. That was a good way to wake up.
When I lived in Indian Rocks Beach, we got evacuated for Irma. So I was in a church for like, I think it was like 3 weeks because they wouldn't let anybody back on the island. It was ridiculous.
For 3 weeks?
Yeah.
Amazing. Because all the lines down and hey, I was up the next day on a roof pulling logs out of this one guy's roof. It was
Yeah,
a fun time.
They apparently had a bridge. It was some type of failure, but they didn't want anybody crossing the bridge because they were afraid the supports were going to get out. It was like, great.
Jeremiah, can you talk again?
Here.
Okay, no, I'm sorry. I'm trying to play with my earphones. Where does one get headphones?
Amazon.
Where?
Amazon.
Yeah. I'm talking about brick and mortar store, Jeremiah. I need to get this kind of like
Walmart.
right away.
Walmart, Target,
Okay.
pretty much any gas station like Wawa.
And that'll work in my computer.
Yep. Are you using an auxiliary port or is it USB?
What's this?
That would be an auxiliary 2.0, 2 millimeter.
An auxiliary 2 millimeter?
Yep.
Standard headphones, yeah.
Okay, so good. I know auxiliary 2 millimeter. I'll be able 2 millimeter. What's the 2? That's the diameter?
It's the rings around it. So if there's 2 rings, it's a 2.0. If it's 3, it's 3.
And there's also
But-
guitar jacks, which are
Hold on a second.
8 millimeter.
Thank you, Corey. Hold on a second, guys.
Bro, Corey, you have such a high definition camera.
Yeah, I spent too much money on it.
Which one did you get?
It's a Rebel T6.
You have a YouTube channel?
I had a Switch a while ago. I don't really stream anymore though.
Love that.
I was gonna say no ordinary guy goes and gets those kind of headphones and doesn't stream for a little bit.
Yeah, it's facts.
So why doesn't this work?
Why'd my camera turn off?
Why doesn't this work?
I like your headset.
Thank you very much, Chris. You see, I'm sorry, are you saying this? I don't even know where my picture is.
Yes, I see it.
Why
That's
doesn't
a
this
3.
work? That's a 3 ring?
Is it too big or is it too small?
I don't know. It doesn't work.
It should definitely work.
Maybe you're
Those are Apple headphones.
Yeah, they
No.
probably have the
You
combo
can't hear
mic
me,
jack.
can you?
I can hear you.
Corey, I see you. Can you hear me?
I can, yeah.
Yeah. We can hear you.
Can you hear me? Anybody?
Yep.
No.
Oh, I don't think he can hear us.
Tell them to
That-
try to clean it.
That port is probably too small.
Or
It might
he,
also be that
missing-
he has there are 3-prong headphones.
or he
and-
should
Yeah,
try,
it's a
or he should
missing
try
a
to,
ring.
or he should try to clean it.
It might be that.
That's true
So
too.
you guys
Those
can't
10
hear me, right?
We can hear you. Yeah, so what's happening is his microphone ring is hitting the connector before the audio. So the audio is like missing that ring entirely.
Okay, so these
So-
are worthless, right?
Yeah.
Okay, so I got to go and get a 2-ring circus as opposed to a 3-ring.
Yep, that's a safe bet.
Okay, fine. I could do that. Now, why aren't I seeing everybody? There we go.
Well, it's only 520.
It's all, yeah. Okay, yeah. What are you doing here yet? I was expecting you to show up about 15 minutes late, Corey.
Well, you know, I don't have to drive, so it's usually my underestimating of the traffic that gets me in late.
Chris, why do you have the Golden Gate behind you?
No, I don't.
Yes, you did a second ago.
What do you mean? That's clearly space.
It was Golden Gate a second ago. I swear to God. I wouldn't lie to you, Chris. There's a
don't think
beach
so.
behind you now.
No, it's space.
Don't play with my mind. It's an easy thing to lose. We doing okay, guys? Oh, shit. Excuse me. That was a slip.
Language.
Yes, I know. I have the extra credit. The extra credit problems. I will put them on the email tonight. Okay. Have until Sunday to finish it.
How many points?
I don't know. I've forgotten. What did I tell you?
You didn't tell us a number.
Yeah.
Then 2.
Okay.
I think Chris is gonna rob you.
I don't remember what I said. I really don't. If I have to, I'll go back and re-average the tests. I don't know off the top of my head. All right. Are you laughing at Chris, Carly?
No, I guess the whole conversation is just kind of funny.
I'm laughing at Chris.
What you expected chemistry?
I don't know. I also just laughed pretty easily too, so.
Chris, I am going to ask you to stop that once the class begins. All right.
All right.
Just feel free to have fun for 5 more minutes.
I'm just getting used to the software. It's kind of a steep learning curve.
Now, come on, guys. You've been doing this for what now? How many semesters is this for you guys? 5 semesters? Dealing with
What?
this crap?
No, like a 3 or 2.
Well, no. It started last spring. So if you went last summer, spring, summer, fall, spring, summer, that's 5 semesters I'm counting.
I wasn't in school for any of them. This is my first back after Rona.
Oh. Good.
But
So that's great, Corey. How much further do you have to go then?
this is my last semester here. I'll be transferring to UF probably.
Should make Chris happy.
Yeah, we're gonna be in the same classes, I think.
Oh, good. Engineering?
Yeah. Mechanical.
None of this chemistry crap.
Yeah, I was thinking about material science, but they required Chem 2, and
I believe me, I've seen chem engineers cry at PChem. It really is a sad sight.
What class?
Physical chemistry.
Oh, I don't even know it.
It's think about thermodynamics. It's an entire semester of thermodynamics in calculus form. It's real fun.
I'm gonna check if I have to take that.
Probably not.
Avoid
I
it
don't
if you
know.
can. It's the only class I've ever been in which I could not tell you half the time what was going on. I mean, I had a program and everything, and it was still off kilter.
I want to see if I have to take that.
You do have to take it, Chris?
I'm checking right now.
Oh, I can see I'm going to have your divided attention this entire evening. I got 10. I got 10 of you in here. So it's kind of an important day because there's a lot of stuff we're going to go back through periodic tables. We're going to go apply quantum mechanics to periodic trends. That's the first thing we're going to do here. We're going to get into a little bit of bond energy chemistry. It's going to be a little bit of thermodynamics, but straight through the bond chemistry. And you're going to have to pay attention a little bit to the way it gets taught because it's different from Hess's law. And then we're going to end up with Lewis dot structures. And again, that's another thing that a curve gets thrown on. So I'm stopping share and we're going to get to the PowerPoint. As long as I figure out which PowerPoint I'm supposed to be at. Are you seeing the PowerPoint, ladies and gentlemen?
Yes.
Are you seeing the PowerPoint? Somebody shake their head.
Yes, we do.
Wonderful,
Yes.
wonderful. Okay, so we're going to start the slideshow and get us all going. All right, now, what happens when you have these electrons orbiting in shells that are underneath the outermost shell? What happens is the outer shell electrons, the inner shell electrons screen for the outer shell electrons. It's much like if you have blockers that are keeping the defensive line out. The electrons that are inside of the valence electrons shield the valence electrons from feeling the full effect of the protons in the nucleus. But if you have more rushers than you have blockers, you're going to get people that seek through. So in that way, the quarterback, the outside electron, has to be concerned with the extra blockers or the extra rushers that are coming in. So we have to realize that the valence electrons are screened somewhat by the inner shell electrons. So that if I have a sodium nucleus here, if I have a sodium nucleus here, I can tell that because it's got 11 protons. So if I've got 10 electrons on the inner core, and that last valence electron gets screened by those 10. So in effect, all it's really feeling is the effect of one of the electron, or one of the protons. And that's all it said in the first couple things. So basically, you can figure that out by just saying the effective charge that's felt by the valence electrons is the total number of electrons minus the screening electrons. And basically, that's the number of the inner electrons for all intents and purposes. So we have to keep that in mind when we're going through some of these periodic periodic trends. First thing we're going to get onto are the size of atoms. And basically what you want to think of as the size of the atom, it's half the distance between two atoms that are bonded to each other. That is the size of that atomic radius. Now, it's very easy. When you're going up and down the periodic table, it's easy to see that as you go down the periodic table, you're adding another row of electrons out there. So as you add that other row of electrons, what's happening is the molecule is getting bigger. So as you go down the periodic table, you are increasing the size. Now, as you go from left to right, what is happening is the valence electrons are essentially seeing more of the effective, more of the charge that's coming from the nucleus. So as you go across, it's feeling more positive pressure. So that sucks the negative electrons in further, which means that the size decreases from left to right. It depends on nuclear charge and number of electrons and the orbitals in which they reside. Why do you think cations are smaller than their parent compounds? Why is magnesium +2 smaller than magnesium?
Because it has
Because
less
the outermost electron is removed and repulsions are reduced.
that.
Couldn't have said it better than my, oh. Thank you. Thank you very, very much. Well, if you think about it, the easy way is if you take those two outer electrons away from magnesium, you've lost that outer shell of electrons. So the cation has to be smaller. On the other hand, anions are larger. Again, you have more electrons, it's going to repulse more. If it repulses more, they are going to be larger than what their parents are. Cations smaller than the parent, anions are larger than their parent. In an isoelectric series, ions have the same number of electrons. So if I'm dealing with oxygen and fluorine, I don't know why they put the slide in here the way they did, because the isoelectric series is not lithium and beryllium, but it is sodium and magnesium. Sodium and magnesium have the same number of electrons as oxygen and fluorine. They all have 10 electrons. Now, as you are increasing the nuclear charge, you are decreasing the size. So if I have sodium and magnesium out here, they have the same number of electrons, but they have more protons. So sodium and magnesium are going to be smaller than fluorine and oxygen. Fair enough? Make sense, guys? I like this slide. The slide makes a lot of sense to me. Increases going down, increases going from right to left. The right to left is because the ones on the right have more effective charge. The reason they're larger on the bottom is we're increasing the number of shells. Said all this before. So Grace, do you have a periodic table near you? Grace?
Oh, I didn't hear you said my name. No, I don't, but I can pull one up.
Who has a periodic table? Pull it out, guys. We're doing periodic trends here.
Well, now I do.
Thank you very much. Okay. Chlorine.
Okay.
Number 17,
So-
potassium, 19. Selenium, 34. Rubidium. Good God, where the hell is rubidium? Sorry, 37. And GE, I don't even know. G, you know what G is? G, I don't know what it is. Germanium, 32. You got all of them, Grace?
Sure. Okay.
Increasing atomic size.
Okay, so
We want the smallest first.
the smallest first. Okay. The smallest first would be chlorine,
Bingo.
and then sorry, this is kind of hard on my computer. And then Se,
Bingo.
and then potassium.
Nope,
Wait,
you
no.
missed one.
No, wait. Se.
Nope.
Wait, I got-
Se was, you were right. Chlorine, potassium. I'm sorry, excuse me. Chlorine was first. Then you said selenium.
and then Ge,
Germanium.
and then what's left? Rb and potassium. So then it goes potassium and then Rb. Right?
Bingo. Absolutely. Okay, Chris. The bottom row there.
Yeah.
From increasing atomic, from smallest to largest.
The smallest is going to be I'm gonna go with N. I'm gonna say N-3.
It's the largest.
Yeah.
That's what I heard you say. Didn't I hear you say the largest, Chris?
Yeah.
Okay. What do you think would be next?
N-2.
I said you were brilliant and smart in spite of yourself. Go ahead. Continue on, Chris.
I'm confused.
Okay, the N-3 is the largest because it has the most electrons and they're repelling each other.
Right.
Okay?
Yeah.
So N-2 would have the second largest amount of electrons.
Right.
Okay? So what would you think, going along this trend, what do you think is next?
But my question is like, aren't they on the same shell though?
They're in the same shell, but
So-
Chris, the electrons want to repel themselves. They want to get as far away from each other as possible. So they're going to max out their distance.
Right. But my question is like, they're maxing out their distance from each other within the shell though, no? Like they're going outside their shell?
They're
And that's-
repelling each other.
Right, I get that they're repelling each other. Right? But how does that increase the size is my question.
Okay, because they remember the electrons, if all things are equal, they're going to be all over the orbital shape, right, Chris?
Right.
But all things are not equal. N-3 has more electrons. So they're going to occupy more of the outer space of the orbital than, say, something like N.
Okay, I mean, this is like, so the orbital has like a width to it, is what you're saying. Like, let's say I had a spherical orbital, it has a width to it, and the more electrons, the closer to the outer bounds of the orbital they'll be.
Remember, Chris, if I have an S orbital, it can be anywhere.
Right.
That breath I just took, the electron from that carbon dioxide molecule can be in your house right now.
Yeah.
So there's no limit.
All right.
And
I'm
if
just gonna-
these things can be as far apart as they can, they will be.
Okay. I'll just say n-3 is the largest, and then it just goes down. So like n-2 is second, and n+1, n+3.
And the reason the n+3 is it's not feeling as much its shield.
I'm sorry, what'd you say?
And there's not as many electrons in it to shield the other electrons from the inner core.
Okay, so what? Okay, that makes sense. So the
Okay.
orbital kind of changes depending on the isotope.
Those are an isotope, depending upon the ion.
Yeah, that's what I meant. The ion.
Okay.
Okay.
We good, Chris?
Yeah.
All right. Now this is going to be a little more funky than the shape. By definition, ionization energy is the amount of energy required to remove an electron from an atom or ion. Okay? That's by definition. Jeremiah, do you think it's easier to take the first or the second electron away from an atom?
Probably the second.
It's harder because you have an ion now. You have a positive charge on that atom.
Gotcha.
So that atom wants to cling on to its electrons more. So the second ionization energy is always going to be greater than the first. Third is going to always be greater than the second, and so on and so forth. And they're designated as first ionization energy, second, and so forth. Now, you're right. As soon as you take, if you go to the right, each succeeding electron that gets removed takes more and more energy. Are you seeing that trend, ladies and gentlemen? Corey, you got it? All right, now, some trends seem to be an astronomical jump. We have sodium going from its first ionization energy to its second. That's a jump of 10 times the energy. Magnesium, the jump from the first to the second is not so bad, but pulling that third one off is another astronomical jump. Carly, can you give me an idea why you think this is? Carly?
I'm not quite sure.
Not quite sure is a good answer. Throwing it out there. Can anybody see what's happening here? We have sodium. Its first ionization energy is low. Its second one is very, very high. Magnesium's first and second are normal. Its third one goes very high.
I'm going to guess that it has to do with the valence electrons. And
Very good, Maggie. Very, very good. Absolutely. Because look, if I take one electron away from sodium, haven't I gotten rid of its valence electron? And I'm real happy. I have 10 electrons. I've got a full shell. So it's going to take even more energy to pull that off. So once we go and leave once we leave a shell, or even once we leave an orbital, there's going to be an added kick. Does that make sense to you guys? So when you've removed all the valence electrons, the ionization energy takes a quantum leap, so to speak. As you go down the column, less energy is required. This is basically because they're further away from the nucleus. The Z effective is essentially the same for each of the elements in a column. But the thing is, the valence electrons are further away from the nucleus, So it becomes easier to just grab them. Now, if we're looking at the ionization energies, there's some things that seem out of place here. My first ionization energy goes down for the third element, which is boron. Beryllium has a higher first ionization energy than beryllium does. Then we go to carbon. I'm sorry. This one is, can you see the arrow, by the way? This, we go lithium, beryllium. Then we go down for boron. And guys, get out your periodic table. You're going to need it. We go down from beryllium to boron. Then we go back up for carbon, back up for nitrogen. Then oxygen's ionization level goes down. Then it goes back up for fluorine and neon. We seem to have this trend where the third element goes down in ionization energy, and the sixth element goes down. Anybody fathom a reason? Let's think about quantum mechanics. Let's look at beryllium.
Does it have to do with the first electron into an orbital is easier to remove?
Bingo. Look, if we go from beryllium to boron, the electron is filling in. The next electron in is going into the 2p orbital. 1s by itself has a stability to it. So it's easy to remove that one electron in the ps and the 2p orbital. Now let's go to nitrogen. Okay? Think about what's happening, how we're filling the p orbital. Aren't we filling into each one of those suborbitals one electron to make nitrogen? I got to get this to see if somebody's missing. Hello? Are you wasting my time? Yes, you are. I'm teaching a class right now. Bye. Sorry, there's always the off chance that somebody's waiting to get in here. Okay, so if you've got your periodic table out, and I'm putting electrons in for nitrogen, I'm putting one into each one of the 3p orbitals, right? That fourth electron has to be paired up. And it doesn't want to be paired up because it's put in a small little compartment with another electron. They don't like each other. So it becomes easy to remove that extra electron that goes in there. Does that make sense, guys? And this is basically what's occurring between magnesium and aluminum. Magnesium, aluminum. Again, I'm putting an extra electron in the p orbital. It doesn't take that much energy to take that out. Then I'm going to phosphorus and sulfur. Up here, phosphorus and sulfur. Phosphorus has 3 electrons in it. Sulfur has to put another electron to pair it up. It makes it electronically unstable to do that, so it's easy to remove that to make it satisfied with the half-filled shell. Again, is this making sense, ladies and gentlemen?
So is it always the third, like over?
It's for ionization energy. It is always the fourth one going into the p orbital, or the third one, or the first, either the first one going into the p or the fourth one going into the p.
Okay.
Now, it gets messy. When you get out here, there are many. The more electrons you have, the more strange things you have happening with the electrons. So as a consequence, it's not as straightforward when you get beyond here. But it all has to do with stability. Okay, that was ionization potential. Ionization potential, it is just as you go up the chart, it's harder to remove an electron. As you go from left to right, it's harder to remove an electron. As you go up the table, it's harder to remove an electron. Now, another property is something called electron affinity. It's the energy charge accompanying the electron addition to the element. So it's adding an electron to chlorine. And as you might expect, as you go from left to right, there is a general increase in exothermic reaction when you add an electron. As a general rule, when you go from left to right, the electron affinity becomes more exothermic. And again, it's because the guys over here, the guys on the right side of the periodic table, want the electrons. They want to fill out that shell. The guys over on the left side, they don't want it at all. It's hard to put an electron onto lithium. Again, there are trends we can notice. It's a lot harder to put an electron on lithium than it is beryllium, because we have made a full orbital. Again, going from carbon to nitrogen, think of what's happening to the p orbitals. I'm filling in that third orbital. Again, there is stability. There's stability in a half-filled orbital. Going to fill the entire one, going from fluorine to neon, becomes very, very easy. So basically, the properties are based upon their electron configuration, and these properties can be rationalized by employing the quantum mechanics to the individual atoms. Are we okay so far? Am I making sense? Now, there are three types of bonds. We're going to get into ionic, covalent, and metallic. And ionic bonds are simply one of the atoms has stolen an electron from the other, and there is an electrostatic attraction between the positive cation and the negative anion. In a covalent bond, we have a sharing of electrons. And the third type of bond that really doesn't get talked about a lot are metallic bonds. And basically what metallic bonds are is a sea of electrons. And the electrons aren't really owned by any of the individual atoms, but they're owned by the whole conglomerate, which allows for easy transfer of electrons which allows for conductivity. Now, when I'm dealing with ionic bonding, okay, remember in the periodic trend of ionization potential, it takes energy to remove an electron away from sodium. We get back energy by giving the electron to chlorine. But look, it takes 495 kilojoules per mole to remove the electron from sodium, but we only get 349 back. There's got to be something else to the puzzle which allows for the exothermic reaction of bonding sodium with chlorine. And the reason comes in because of something called electrostatic attraction. What happens is the sodium loses the electron, the chlorine gains the electron. But there has to be energy that attracts the positive sodium with the negative chlorine. And that is called something called lattice energy. And lattice energy is nothing more than the energy required to totally separate a mole of cations from a mole of anions. And it's associated with something called Coulomb's law, where the energy is equal to a constant times the charge on the first ion multiplied by the charge on the second one divided by the distance between them. Okay. Let me see who want to give this. Maggie, do you have your periodic table there, Maggie? What's
Yes,
bigger?
I have the periodic table.
What's bigger, chlorine or bromine?
Bromine.
What's bigger, sodium or potassium?
That means I have to find them.
On the left side of the periodic table.
Sodium or potassium's bigger.
Potassium's bigger. So if I have potassium bromide, which you just said were bigger atoms, and I compare that with sodium chloride, the charges are exactly the same, but the distance is bigger. So the energy attracting sodium to chlorine is greater than the energy attracting potassium to bromine. Does that make sense? Maggie, does that make sense?
So basically it just has to do with the size of
All right, you asked the question, Maggie. Okay, let's look
that was a trick.
Let's look at magnesium and sulfur. Okay? And sodium and chlorine. Would you say that their diameters are approximately the same? Little difference, but approximately the same.
Yeah.
Now, magnesium has a +2 charge, sulfur has a -2 charge. Sodium has a +1 charge, chlorine has a -1 charge. So by my formula, it's not only the distance. If the charges are greater, the attraction between magnesium and sulfur has greater energy than the attraction of sodium for chlorine. So it's a combination of both of those factors, Maggie.
Okay.
Wait, I have a question.
I'm here.
If you go back to the last slide you were on, what's the K?
It's a constant.
Okay. So it's just the top two are the charges, and then the bottom is a distance, and then K is a constant.
Distance between the two atoms.
Okay.
See, it says so right there. Okay. Sorry, these are nothing. All right, what's happening? When we create the sodium, stop it. When we create the sodium ion and the chlorine ion, it takes energy to do that. So we're taking that up. We get some energy back by giving the electron to, oh, I'm sorry. Let me go back here. By taking sodium from a solid to a gas, that's energy in. By taking Cl2 to Cl, that's energy in. When I am taking the electron away from sodium, that's energy in. These are all endothermic processes. What happens in ionic bonding? We get some energy back by giving that electron to chlorine. But the bulk of the energy is the lattice energy that's holding the sodium and the chlorine together. So, as I said before, it increases with the charge of the ions, and it increases with the decreasing size of the ions. As a general rule, guys, don't write these down. You're not going to be tested on them. But as a general rule, ionic substances are hard and brittle. They have high melting points, and they don't conduct electricity in the solid, but do when they're dissolved in water or in the liquid state. Just some nice to know fun facts. Now we're going to get off on covalent bonding now. If I was going to do bond energies with ionic compounds, I have to employ lattice energy. Covalent bonds are a little bit different. It's a typical bond between two nonmetals. They can be polar or nonpolar, and you can have single, double, or triple bonds. The fact that you've got these electrons being shared sticks the atoms together with one another. And there are several things that are happening in there. You've got the attraction of the electrons with the nuclei, but you also have repulsion of the two nuclei, and you have repulsion of the electrons. This is all going on within the bonding. Now, according to the octet rule, atoms are going to gain or lose or share electrons to get 8 electrons. If I have 2 fluorines, each one of them has an unpaired electron. So fluorine's going to want to stick together and share those electrons. In a single bond, atoms are held together by 1 electron pair. If I have a double bond, that means there are 2 electron pairs between each atom. So there's 2 between this carbon and this carbon and this oxygen, and 2 between the same carbon and this oxygen. If I have 3, there are going to be 3 shared pair of electrons. And if you think about it, oxygen has 2 unpaired electrons. Nitrogen has 3. So nitrogen is going to want to form a triple bond, oxygen a double bond. And all the halogens have 1 unpaired electron, so they're going to want to just have one bond between them. Now, when you have these bonds, some atoms have a stronger electron affinity than others. So the electrons don't get shared equally. If I have F2, those electrons are being shared absolutely equally. If I have HF, the fluorine is going to grab the electrons most of the time, lending to a negative side of the HF molecule and a positive side. Electronegativity, the ability of an atom to attract an electron to itself. These are relative numbers. They generally increase when you're going from left to right. They increase going from the bottom of the periodic table to the top. That one makes sense because you're getting closer to the nucleus. If you're going left to right, you are filling in more of the electrons needed to make an octet. So basically, if we have a pure covalent bond, this is something like FF. The electrons are equally shared. If we have a polar covalent bond, this means one of the atoms is taking charge of the electrons most of the time. If I have an ionic electron, that means one of the atoms has completely stolen the electron from the other. If you have between 0 and 0.5 electronegativity difference, you've got a nonpolar bond. Between 0.5 and 2, you've got a polar covalent bond. And above 2, you've got an ionic bond. This is the difference in the electron negativities of the two atoms. Basically, for ionic, we're talking about metals versus nonmetals. So again, if we're looking at an HF molecule, the electrons are spending more time around the F. You can indicate that by taking an arrow and shooting it in the direction of the fluorine, or you could take these little gammas. I think these are small gammas. And you can put gamma positive on one side, gamma negative on the other. And what's happening when you get a change in the electrons, you get something called a dipole. If you put this molecule in a magnetic field, it will orient itself such that the positive end of the molecule is oriented towards the negative end of the magnet. Don't worry about the formula. Okay. Have I still got you with me at this point, ladies and gentlemen? This is why I really hate teaching in Zoom. I can't be nearly as animated. I'm stuck in this chair. All right. Are we fairly good on periodic trends and understanding the bond energy so far? Because I'm about to break your world. Breaking bonds takes energy to accomplish. It is endothermic. Creating bonds releases energy. It is exothermic. So, when we are looking at an enthalpy of reaction regarding bond breaking and bond forming. We are going to have the sum of the bonds broken subtracted by the sum of the bonds formed. Think about it. Don't the reactants have their bonds broken? Somebody shake their head, yes. Don't the products have their bonds formed? Somebody shake their head, yes. Now, does this seem like it's the reverse of Hess's law? Remember, Hess's law said sum of the enthalpies of the products minus the sum of the enthalpies of the reactants. Do you remember that, ladies and gentlemen? That's what Hess's law was. We are not talking about enthalpies. We're talking about bond energies. So in this case, we're dealing with sum of bonds broken minus sum of bonds formed. The difference is, does anybody see any negative signs? Any negative signs in any of these bond energies? That's because this is showing you the bonds breaking. This is the energy of these bonds breaking. If the bonds get formed, we have to subtract them. Does that make sense? If that doesn't make sense, then you literally have to just write it down somewhere that when you're dealing with bond energies, it's bonds broken minus bonds formed. And the bonds broken come on the reactant side. Bonds formed come on the products. It is the exact reverse of Hess's law, but it's for different reasons. Maggie, don't you dare yawn on me. I'm going to have to go through it. Chris, this is where you usually pop up.
What?
What? Chris, show your face. Tony, Kyle, Marin, Aditya, show your faces. Alexis, Michael, Luke, show your faces, guys. I want to see them because I want to see that dumb look on your face when you're totally lost. Come on, everybody picture up. Thank you, Aditya. Tony, Luke, Alexis, Michael. Both Michaels probably. Thank you, Tony. Thank you, Michael, Luke, Alexis. Thank you, Alexis. Luke, you're still not there. Chris, you're going to let my last comment go unchallenged.
I don't know what you said. I'm not gonna lie.
Okay. Do you see this screen that's up there now?
Yeah, it says the change of heat is the sum of the change of heat of the bonds broken minus the sum of the change in heat of the bonds formed.
Okay. Now, bonds broken occurs in reactants. Bonds formed occurs in products.
Yeah.
It is the reverse of what's happening in Hess's law. But in Hess's law, we're dealing with heats of formation. We're not dealing with bonds. That is the difference. So you're going to have to write down somewhere. Hess's law, sum of products minus reactants. When I'm dealing with bond energies, it's sum of the bonds broken minus sum of the bonds formed. And the bonds broken are going to be the reactants. Bonds formed are going to be the products.
Yeah, that makes sense.
Do I have any questions about that? you're going to get a chart like this with every question that you have involving these. Now, I got to look at my overall reaction. I've got two H2s plus O2 yielding two H2Os. Each one of my hydrogen molecules has an HH bond. So since I have two molecules, I have two HH bonds that need to be broken. My oxygen, I have one oxygen molecule. I need to break one OO bond as well. So I've got my HH bonds are 436. My OO bonds are 146. So I'm going to take my 2 times my 436 and add it to 1 times 146. Now, when I'm looking at water, water has a hydrogen bonded to an oxygen, which is bonded to another hydrogen. So each water molecule has two OH bonds. I have two molecules. This means I have 4 OH bonds being formed. So I have to subtract them because those bonds are being formed. So I have 4 times 463. That gives me 1852. I subtract that from 1018. That gives me negative 834. That's to create two molecules. Or in other words, 417 kilojoules per mole. That works out very nicely with the heat of formation of water.
So why is there 4 OH bonds? Because if
Okay, I'm sorry, who's asking the question?
Grace.
Grace. Water. In a water molecule is an H bonded to an O.
Yes.
Is that O bonded to another H?
2 of them.
It's bonded to two H's, right?
Yes.
So in each water molecule, there are two OH bonds.
Okay.
But my formula says I have two waters.
Oh, okay, got it.
So this is four OH bonds are formed.
I have
Got
a
it.
question.
I'm here.
There was a problem like this on the homework.
Yep.
And it told you to balance the equation, but instead of just giving us like the actual balanced equation, it had like a coefficient of 1, and then it had a coefficient of 3 halves, so 1.5. So like naturally when I did it, I multiplied the 1.5 by 2, and so I got the entire balanced equation. But like in the answer, it put the balanced equation as 3 halves, and it made all the numbers wrong. Because instead of multiplying something by 3, I had to multiply it by 1.5 and like obviously multiply all the other ones by a smaller factor.
Did it ask you what the heat of the reaction was?
Yeah.
Okay. Did it
I
ask
have
you?
pictures of it.
Ask me later. I need to see the specific thing, okay?
Okay.
This is Chris, I guess, right?
Yeah.
Ask me later, Chris, okay? Even
All
stay
right.
after class for it if necessary. Okay?
I
Go
have
ahead.
one more question.
I'm here.
For the answer, it says positive 417. Is that supposed to be negative?
It's supposed to be negative.
Okay.
Okay. We got to look at this. Slideshow. This is my reaction. CH4 plus Cl2 yields CH3Cl plus HCl. What bonds am I breaking?
The CH4 and the Cl2.
Okay. How many bonds am I breaking in the CH4?
4.
Am I really though?
No.
Because
One.
how many am I really breaking?
Oh, 3. 1. I don't know. Never mind.
How many of the H's are replaced?
3 of them.
Are they?
4 of them. 4 of them.
Are they?
I don't know. I don't know. Never mind.
Well, look, don't give up. Don't give up. I want you to see this. Can you see that the CH4 is being turned into CH3Cl?
Yes.
So in reality, only one of the CH bonds is breaking,
Okay.
and it's being replaced by a CCl bond. If you want to, it's not going to hurt. If you want to take 4 CH bonds, that's fine. Go ahead and do it. Because you're going to be subtracting 3 of them out later on. Does that make sense, guys? Guys, I need to take a 5-minute break. I'll be right back. Aditya.
Hmm?
Can I ask you a question, Aditya?
Sure.
How can you do so well in lecture and not do as well in the lab? What's going on here?
Have you not been joking this whole time? Like all the time you talking about like lab? Like I thought you were joking. I'm not in your class.
You're not in my lab.
No, you've got me messed up with some other kid. I thought you were joking this whole time.
No, I wasn't, Aditya. I'm sorry. I swear to God, I have another kid named Aditya in my lab,
That's good to know.
and he's doing horrible.
Mm.
Okay. Are you joking with me now?
I am not joking with. I'm not in your lab class.
Oh, God. No problem. Okay. Who was just arguing with me about the CH4 and the CH3Cl?
Grace.
Is that a less? So who's me?
Grace.
Don't ask me. For God's sakes. You know how many me's there are in this class?
I said my name.
Okay, Grace.
Yes.
If you want to, if it's going to make you feel better. Okay? Break all 4 bonds here.
Okay.
Because ultimately, it's not going to matter. So if you say that you break 4 CH bonds, how many Cl bonds, Cl bonds are you breaking? Here's the molecule, Cl2.
1.
You're just breaking 1. So if you want to take 4 times 413 and add it to 1 times 242, that's fine. That's fine. But you have to realize you're going to be subtracting out 3 of those CH bonds because those are formed back again. Does that make sense, Grace?
Yeah.
If you'd rather do it that way, you're not going to come up with the wrong answer.
Okay.
But I'm going to choose to do it. I'm breaking only 1 CH bond. And I'm breaking 1 Cl bond, Cl bond. So these are the bonds that are broken. Those go on the left side of the minus sign. I am forming one CCl bond. And I'm forming one HCl bond. Remember, I'm subtracting these guys. And I am adding up these guys. All these numbers are positive. I do that math out. And I get 1 times 242 plus 1 times 413. From that, I subtract out 1 times 328 and 1 times 431. Add all those numbers up, I get a negative 104 kilojoules per mole. Anybody having problems with this? Michael, Luke, I need to see your faces.
Luke doesn't have a video on his laptop.
Okay, that's fine. Dara. Hi, Dara.
Hi.
This compound has a carbon with 4 hydrogens attached to it. This is oxygen attached to another oxygen. This is carbon with a double bond to oxygen and another double bond to oxygen. This is H to O to H with another H to O to H. Do I have any CH bonds over on the right side? So I got to break how many CH bonds on the left side? How many do I have?
1.
I have 4. 1?
1.
No.
4.
You have to break all of them.
Yeah. Dara, aren't all 4 hydrogens bonded to the carbon?
Yeah.
So I have no CH bonds over here, so I got to break all of them.
Okay, yeah.
So I have to multiply 4 times 413 for bonds broken. How many O's do I break? How many OO bonds do I break?
I don't know.
I don't know is a great answer. How many oxygen molecules do I have? Say it.
1.
1. I only have 1.
Okay.
And that one molecule has how many bonds between the 2 oxygens?
Wait, could you repeat that?
That oxygen bond has how many oxygen bonds does the O2 have?
1.
Just has 1, Dara. So I'm going to take 4 times 413, and I'm going to take 1 times 146. Okay? Tony, do you remember what I said this structure looked like? Carbon in the center, 2 double bonds, and an oxygen on either end.
Mm-hmm.
So how many C double bond O's do I have?
1.
Carbon in the center, double bond oxygen on the left, double bond oxygen on the right.
Also 2.
I have 2 C double bond O's. So I'm going to take 2 times 799. But those bonds are formed.
Mhm.
Michael Cassis, I have water here. Do you remember how I described it before?
Not necessarily.
Okay. Water has an oxygen in the center.
Mm.
It's bonded. That oxygen is bonded to 2 hydrogens. So in each molecule of water, how many OH bonds do I have?
Just one.
There's an oxygen in the center. 2
So then two
hydrogen. There are 2. So, but how many molecules do I have, Michael?
3.
Oh,
2.
2. I have 2 molecules. Each one of the molecules has 2 OH bonds.
Okay.
So I'm going to multiply my my HO bond, my 463. I'm going to multiply that by 4.
Gotcha.
At this
I have a
point, I
question.
just add everything up, do my multiplication, add everything up, and this turns out to be negative 1,305 kilojoules a mole.
I have a question.
I'm
As
here.
well.
The CO2 you said was double bonded?
Yes.
Wouldn't, like, why isn't that 4 then? Times 4. Isn't it 4 CO bonds?
It's 2. No, it's if you notice, the C double bond O has a different energy than the CO bond. CO
Oh,
bond is
okay.
358. C double bond O is 799.
Got you. I was thinking, I clearly wasn't looking at the table very detailed. Thank you.
I also have a question.
I'm here.
How is this equation balanced? It doesn't seem balanced to me. It seems like on the right
1
side.
carbon.
No, the oxygens.
Ah, you're right. You got me. Ah. You got me. Who was it? Who pointed that out?
I did.
Don't say I did. You know how many I dids I have in my class? Who is I? If you want extra credit, you'll give me your name.
My name is Chris.
Chris who?
Horsa. HORSA.
There's nobody by that name in my class.
Is like I get all the homeworks and everything too.
Okay, yes, you were right, Chris. I did not balance that correctly. That should have been a 2. That should have been a 2. And this should have been a 2. And that makes this final number a little less than that.
Mr. P,
Yep, I'm here.
Carly's Wi-Fi went out, but she said that it might come back on, but you might have to let her back in a little bit.
Okay, I promise to do so.
Okay.
I'm sorry, this is 9.
She's in the waiting room.
Okay. Last problem in this regard, guys. Okay. I've got N2O plus N2O yielding 4 N2s plus O2. Okay. Michael Thompson. Michael? Okay, we'll go for somebody else then. Aditya. How many N double bond ends are being broken?
Two.
I got 2. Okay. How many N double bond O's are being broken?
Also 2.
Also 2. Okay. So I got 2 NNs and 2 NOs. All right. Dara, how many N triple bond ends are being formed?
4.
4. And how many O double bond O's are being formed?
1.
So I've got all that information down there. Each one of the N double bond N, the numbers you see on the right are what it takes to break or form one bond. So all I got to do is just multiply the numbers. Multiply the numbers out, and I end up having a negative 2266 kilojoules per mole. Any questions on that, guys? This is the last problem I have shown for you. The main thing is, this is not the same thing as Hess's law. We've got summation of the bonds being broken minus the summation of the bonds being formed. Are we good now? Okay. And I'm going to stop share. And we're going to get to my other PowerPoint. I don't believe I did that. Crap. Okay, I'll be back in a second. Or I'm going to stay here. I just have to find chapter 10. I had it all prepared, but then I screwed up. We're going to do a different thing. Oh, Lewis. Lewis is a very famous man. He came up with a way to draw, a way to define bases. Very famous chemist. Also came up with a way to represent chemical molecules. It's brilliant. He figured those inner electrons don't mean anything anyway. Why do I have to draw them? So he didn't. He basically decided, okay, it's only the valence electrons that counts, so that's the ones that I'm going to draw. So if I'm looking at an atom of oxygen, by the way, are you seeing my screen?
No.
You didn't post it yet.
Okay, now are you seeing it? Now are you seeing the screen?
Yeah.
Okay, so he came up with this brilliant idea that all I need to do is show my valence electrons. And the way I'm going to do that is I'm going to draw it in a very specific manner. If I have oxygen, I'm going to draw it on 4 different sides. I'm going to put 1 dot on each side. Then I am going to pair up. And the reason this is brilliant is because right now you can tell me how many things can bond with oxygen. If I tell you that bonds are sharing unpaired electrons, how many bonds can oxygen have?
2.
How about nitrogen, which is just below it?
3.
3. So just by drawing these structures, we know how many things can be bonded to oxygen or nitrogen. Now, I'm not going to go through this. Sodium would have 1 electron. Phosphorus is just below nitrogen, so it also would have 5, just like nitrogen does. Bromine would have 7. All I'm doing is putting dots around the elements. Did everybody see that, or do I need to actually have you demonstrate it for me? Are you with me, or I'm trying to skip some steps here, guys? We good, Kyle? 1? 1. Are we good? You understand what I was doing?
I was opening this PowerPoint. Yeah.
Okay. Now, Lewis also said, okay, if I can do elements, I can also represent molecules. And the way I'm going to represent molecules is I'm just going to put a pair of electrons to indicate that a bond has formed between the 2 elements. So if I have carbon, my carbon would have 4 individual electron dots around it. In order to draw the methane molecule, I would have a hydrogen come in and donate its electrons so that I get an electron pair between this hydrogen and this carbon. I have another one on the right. One of the electrons is donated by hydrogen, one by carbon. The hydrogen below, same thing. The hydrogen on the left, the same thing. So I can represent molecules in the same way I can represent atoms. Everybody buy that? Alexis, you buying this? All right. Now we're going to get into the rules. The rules for drawing Lewis dot structures. From the molecular formula, write down the elements. Generally, you want to put the least electronegative element in the center. Next thing you do, you add up all the valence electrons. Account for charges. If you're given SO4 2-, then because of the 2-, you have to add in 2 electrons. If you are given NH4+, you have to subtract 1 valence electron from that since you have a plus charge. So step 3, you add up all the valence electrons. Step 4, put 2 electrons between each of the elements. These are going to indicate at least a single bond between all of the elements. Subtract the amount of bonding electrons, the ones you just used. Electrons that are between the elements are called bonding electrons because they indicate that there is a bond being formed. Subtract the bonding electrons from the total number of valence electrons. Step 6, 1, fill the valence electrons, fill the terminal atoms with pairs of electrons. Note, because hydrogen only needs 2 electrons, it will not take any more. The 2 electrons around hydrogen are fulfilled by the bonding electrons. Subtract. You just put lone pair electrons around all the terminal atoms. Subtract the lone pair electrons from the remaining ones. If you have any leftover electrons, they go on the center atom. If the center atom does not have 8, take a lone pair from one of the terminal atoms and place it between the terminal atom and the central atom. You've created a multiple bond. Don't worry, these rules are going to be repeated. Last step, make sure everything has 8 electrons around it. Note, if you have a hydrogen or a halogen, they can only make one bond. And since they can only make one bond, they end the chain. All right,
Can you say that again? Hydrogen and halogen, or hydrogen and
hydrogens and halogens. Okay, each halogen, chlorine, iodine, fluorine, and bromine. Each halogen has 7 electrons around it, so it only has 1 unpaired electron. So it can only make 1 bond.
Okay.
SO2. First, rule 1 and rule 2. I got to write the elements down, and I want to put the least electronegative in the center. What's the least electronegative? Sulfur or oxygen? 1.
You say the least electronegative.
Least electronegative, sulfur or oxygen?
Oxygen.
Take a hint from what I've written on the screen.
Oh, sulfur.
Sulfur is less electronegative than oxygen. I'm going to put it in the center. So rule 1 and 2, I wrote the elements down. I put the least electronegative in the center. Now, I'm going to add up all my valence electrons. There's no charge on SO2. It's free. Bad joke. There are 6 valence electrons on sulfur. There's 1 sulfur atom. So 1 times 6, I have 6 valence electrons. 6 valence on oxygen, but there are 2 of them. So 2 times 6 is 12. 12 plus 6, this gives me a total of 18 valence electrons. Rule 4, I got to put 2 electrons between each of the elements. So I put 2 between sulfur and the left oxygen, and I put 2 between sulfur and the right oxygen. I had 18, I just used 4. So I have 14 left. I just subtracted the bonding electrons from the original number of valence electrons. I got 14 left. I'm going to fill the terminal atoms with pairs of electrons. Oxygen had 2 bonded to sulfur. Oxygen can take 6 more. The right oxygen also had 2 bonding already, so it can take 6 more. After subtracting out the bonding electrons, I had 14 left. I have just used 12 of them. So I have 2 remaining. The 2 remaining go around the center atom. But if I look at this molecule, My sulfur only has 6 electrons. My oxygens are fine, but my sulfur only has 6 electrons. I have to fix that. The way I fix it is I take 2 electrons from one of the terminal atoms, it doesn't matter which, and I put it between the sulfur and the oxygen. That gives me my Lewis structure. Rule number 10, count to see there are 10 electrons around each element. My left oxygen has 4 bonding electrons, 2 lone pair or 2 pairs of lone pair. 2 pairs of lone pairs for 8. My sulfur has 4 bonding electrons to the left oxygen, 1 bonding pair of electrons to the right one, 1 lone pair for 8. The right oxygen, 3 lone pairs of electrons, 1 bonding for 8. I'm good. Any questions here, ladies and gentlemen?
Yeah, I have a question.
Yes, Chris.
So last unit you said that like so like a valence electron is just like the electrons in the outer shell, right?
Yes.
But last unit, like I asked you, and you said like as the molecule, as we increase the size of the molecule, the number of valence electron, not valence electrons, but like the number of electrons in the outer shell increases, and went from 2 with hydrogen to 8, and then to 10, and then to 14, and those were the outer shells, like the last shells.
Okay, it goes 2, 8, 8, 18, 36.
Right, but those are the outer shells. So those are the valence electrons. But then why are there only 8 of them in like the elements?
Okay. All right, Chris, do you have your periodic table with you?
I do.
All right, look across. We're going to deal with the 4th row down, the 4s, right?
Yep.
All right, it goes calcium or potassium, calcium, 4s, correct?
Oh, okay. I understand now. Okay. Yeah.
Scandium
yeah, it makes sense now. Okay.
Scandium to zinc are in the 3D, which is in a lower energy level.
Okay. Yeah, that makes sense. Thank you.
Any other questions, ladies and gentlemen? Last step, check it, make sure everyone has 8 electrons around it. This one does. I hate dots. I cannot stand dots. Dots suck. Do you know why dots suck?
Why do they suck?
Okay, that's a Lewis dot structure. Now, are these strings dots or not? Are they dots or not? Do you know when these things become dots? It's when you've got a test and you're trying to convince me that they're a dot. That's why I hate dots. It's a lot, plus it's a lot easier. If I want to draw the same thing with lines, I can do it a lot simpler and a lot easier. A line is representative of two dots. It's much easier to draw. And if you're going on to organic chemistry, just get in this is how organic chemistry molecules are drawn. You do not draw organic chemistry molecules with dots. Now, will I accept dots? Reluctantly. But you're going to have a hard time drawing them in the text. You're going to have a hard time drawing. Never mind, you're doing it face to face. Will I accept, by the way, this should be for the two lone pairs. I will accept if you want to do it this way, a combination of dots and lines. You like my new toy? Or if you want to do it the other way, I will accept them always. But if you want to make my favor, you will do it like this. I've seen them drawn any combination of these 5 ways. I prefer it this way, but if you feel it necessary to draw it like this or like this, I will accept it. Just know if you are representing it, a line stands for 2 electrons. Are we good? New share. Okay. We have CO2. What's the first thing we do in a Lewis dot structure?
Write out the elements.
What's going to go in the center? The carbon or the oxygen?
Carbon.
Carbon, carbon, or carbon, oxygen, oxygen. What do we do next? First thing we write down oh, that's a text box. That sucks. I don't need that. Never mind. First thing we do, write down the elements with the least electronegative in the center. Okay. Next thing we do after putting the elements down is we determine the valence electrons. Carbon. Ooh. Carbon has how many valence electrons?
4.
Thank you. How many oxygens do I have?
2.
How many does each have?
6.
So, valence electrons. How many do I have?
16.
16. I've counted my valence electrons. Next thing I do, I make bonds. No, stop texting. No. Whiteboard. I put a pair of electrons between my carbon and my oxygen. So I'm going to subtract out 4 electrons. This leaves me with 12 left. Anybody remember what we do next?
Put the dots.
I'm going to put them around the terminal atom. 2, 4, 6. 2, 4, 6. I have just used up all my electrons. Yet my carbon only has 4. How do I get more electrons around my carbon?
Double bond.
Double bonds. I'm going to take a lone pair from one of my oxygens, stick it in here. I'm going to take another lone pair and I'm going to stick it in there. So I now have oxygen, double bonded, carbon, double bonded, oxygen, 2 remaining lone pairs. Is there something else I could have done? Did I have to choose the lone pairs from each terminal oxygen? Could I have chosen the lone pairs from the same oxygen? Is that legitimate to do that?
According to the homework, it's legitimate.
It is legitimate. I can make a triple bond and a single bond. Anytime I can manipulate double and triple bonds like this, that's something called resonance. Now, do all of my atoms have 8 electrons around them? Do all my electrons, or do all my atoms have 8 electrons around them?
Yes.
I'm done. Questions about doing Lewis dot structures? Okay, I need to get back here to this. Okay. COS. Okay, Jeremiah.
Yes, sir.
What goes in the center? COS.
TOS O is gonna have 6 electrons.
Nope. I need to know what goes in the center.
Oh, C.
So I'm going to put C in the center, O on one side, S on the other. Okay. Valence electrons. How many does carbon have?
Carbon has 4.
Oxygen,
Oxygen has 6.
sulfur,
Sulfur has 6 as well.
okay. So I have a total of 16 electrons.
Yep.
Okay. Angelica, what's the next thing I have to do? I've counted up my valence electrons. I have to start putting electrons in my structure. Where do they go first?
On the outsides.
No. How do I know sulfur's bonded with carbon? How do I know carbon's bonded with oxygen?
So then you start in the middle.
Start in the middle. I got to put a bond. I got to make sure that they're bonded to each other. So I have to put at least 2 electrons between each one. So I subtract 4 from 16. I have 12. Okay, Michael, do you know where the next ones go?
Which one?
My next step, I put bonding electrons between the S and the C and between the C and the O.
Michael Cassis or other?
Oh, Michael Cassis.
Gotcha. So you're gonna put around the terminal.
2, 4, 6. 2, 4, 6. That is 12. Do I have any more, Michael?
No, you do not.
Okay.
But carbon needs 4.
So how do I get them?
You could take from terminal.
I could take a lone pair, stick it in there.
Indeed.
I could take a lone pair, stick it in there. And I would have S double bonded C, double bonded O. Lone pairs out here. Is there any way, can somebody suggest another way this molecule can be made to have a correct Lewis dot structure? How's dinner, by the way, Dara?
It was a cookie.
Oh, sorry. Is there some other way I can make this, write this molecule out, Lewis dot?
You can do the triple bond and then take away electron pair.
Okay, I'm going to put a triple bond there.
I have a question for you.
I have an answer, Maggie.
I'm sure you do. Why don't we start with making sure the center electron has 8 electrons just to begin with? Why are we putting all the electrons around the outside elements and then taking them away and making double bonds and stuff?
Okay, logically, I can't, I don't know whether that's possible or not. I guess it could be possible. I guess you could do.
I mean, just because you
boom,
need,
boom.
you know, you need 8.
I know. I guess you could do this if you wanted. Okay. And then you would have 1, 2, 3, 4. Then you would take this one, put it in here, and this one, and put it in here.
Yeah, it just seems to me logically.
Maggie, if that makes more logical sense to you, then do it.
even
Alright.
skip that step and just make them double bonds immediately.
If that makes sense to you, then do it. The trouble is, Maggie, the way I have it works. I know it does. If you can demonstrate that it works for you, I don't care what method you use, as long as the final answer is correct.
Okay, honestly, it was just a question of like, why don't we do that immediately? But
To be honest with you, Maggie, because I did it the other way. I think that this would probably work.
I have a question.
Yes.
It's Grace.
Thank you, Grace.
So if carbon has 4 valence electrons, why does it need 4 pairs? Because aren't there 2?
Because every atom needs to have at least eight electrons around it, with the exception of hydrogen.
Oh, right. That makes sense.
All right. Grace, I have a question for you.
Oh,
Is there some other way we can draw this to have a totally new molecule other than the 2 ways I've shown you?
You could do the triple bond with the oxygen.
Exactly. I can do this, and this is also a legitimate Lewis dot structure. Okay. Questions, ladies and gentlemen? Okay. I'm going to get into something right now. I'm going to use these 3 molecules to demonstrate it. And I'm going to clear everything. Okay, so I drew these out as C triple bond O, single bond S, and I did S triple bond C, single bond O, and I did S double bond C, double bond O. Are those the 3 I drew, ladies and gentlemen? Are those the 3 I drew?
Yes.
Okay. Which one's the best?
The third one? I don't know.
I don't know is the perfect answer. There is something called formal charge. And formal charge is the charge on the atom as it exists in the molecule. Again, formal charge is the charge on the atom as it exists in the molecule. It is equal to the normal valence electrons minus lone pair electrons. Lone pair electrons, not lone pairs, lone pair electrons, plus bonding electrons. I know it looks like an 8. Divided by 2.
Wait, what was the thing on the top of the 2?
Bonding electrons. BE, bonding electrons divided by 2. Formal charge, the normal valence electrons. When you look at the periodic table, how many valence electrons does it have? Does the atom have? What you're going to do from that, you're going to subtract out. You're going to count the lone pair electrons around that atom. Plus, you're going to count the bonding electrons that attach that atom to another atom. And you're going to take those bonding electrons and you're going to divide them by 2 because they're shared between 2 atoms. Let's look at this first molecule. Let's look at sulfur. Sulfur has 6 normal valence electrons. In this instance, it has 2, 4, 6 lone pair electrons minus 2 bonding electrons. So that equals a -1. Carbon has 4 valence electrons normally. How many lone pair electrons does this carbon have?
0.
And it has 2, 4, 6, 8 bonding electrons. So 4 minus 0 plus 8 over 2 is going to be equal to 0. This oxygen has 6. How many lone pairs does it have? Lone pair electrons does it have? Come on, guys, shout these out. The faster you shout them out, the faster we can go on to something else. How many lone pair electrons does this oxygen have?
2.
Thank you. Who keeps on answering?
Grace.
Thank you, Grace.
Mhm.
Do I have to call on you people? Corey, how many bonding electrons does this oxygen have?
Is it?
Corey, how many bonding electrons does this oxygen have?
I'm gonna guess 4.
How many bonds? 1, 2, 3. Each bond has 2. How many bonding electrons?
6.
So to get the formal charge on that oxygen, it's 6 valence electrons minus 2 plus 6 over 2. I have a +1.
I have a question.
I'm here.
So can't you just like, okay, so you have the bonding electrons divided by 2.
You can just count the bonds if you want. Is that what you're asking?
Yes, that's exactly what I
Yes,
was
you
gonna-
can.
Okay.
Yes, you can, as long as you know what you're doing. All right, this sulfur, do the middle one. That sulfur has how many? Same number of valence. How many lone pairs does this sulfur have? Come on, guys.
1.
2. It has 2 lone pair electrons. Undo. How many bonding electrons does it have?
3.
Undo. It has 6 bonding electrons divided by 2. So this sulfur has a +1 formal charge. This oxygen has how many? How many?
One pair of bonding electrons.
Okay. So that's 1 pair or 2 bonding electrons. How many lone pair electrons does it have?
6.
So that's going to make 6 minus 6 plus 1. The oxygen's going to be a -1. Carbon. It's going to be the same all the way across the board. It has no lone pairs. It has 8 bonding electrons. So it has a 0 charge. Sulfur again. How many valence electrons? How many valence electrons in sulfur? Come on, guys, don't make me
8.
shout. Thank you. How many lone pairs does that sulfur have?
2.
So 4 electrons.
4. 4 lone pair electrons. How many bonding electrons does it have?
4.
So my formal charge on that sulfur is 6 minus 4 plus 4 over 2. It is a 0. Carbon is the same. And the oxygen is going to be 6 minus 4 plus 4 over 2. Now, are you not commenting because you're bored, or are you not commenting because you don't know what is going on? Talk to me.
Little column A, little column B.
Are you understanding how the formula works? You
Yeah.
look on the periodic table, find the normal valence electrons. From the normal valence electrons, you subtract out the lone pair electrons that are specifically on that atom, plus the bonding electrons divided by 2. As somebody just determined, if you want to just count the bonds, that works as well. Now, after you've done all this work, you've assigned formal charges to all the atoms. The first rule, least amount of formal charge. Least amount of formal charge gives you the most stable compound. So of these 3 compounds, this one is the most stable. It is the best charge. It is the best structure. Now, the second rule, the negative charge should be on the most electronegative element. So if I'm looking at between this structure and this structure, which one has the negative charge on the most electronegative element? Do we have vote for number 1 or number 2? Which one has the negative? Thank you very much. The negative charge is on the oxygen. That makes this molecule stabler than this one. This is the best choice. This would be second best. This would be the third best. Now, do I have questions on that? Have you got this all written down? If you want it. because I'm about to rock your boats entirely.
So just to like regroup, so whichever one has the lowest formal charge, like after you add them all up.
No, you don't. You don't add them up, because if I add all the formal charges for this one and add all the formal charges for this one, they're both 0.
So you just look at them and
You
see
just
which one
look
is like
at
the
them.
lowest overall.
Right.
Okay. Gotcha.
And then at the second rule, the negative charge goes on the most electronegative element. Are we good now? Okay. BF3. I'm just going to sit here and somebody's going to tell me what to do.
E would go in the middle, and then F would go on the outside.
Okay. Yeah, I realize you have to understand. I was always horrible at Etch-a-Sketch. Okay. Now what do we do?
You add up the valence electrons, which would be 24 in total.
Thank you. Fluorine's 3 times 7. Boron, 3, for a total of 24. Now what do we do?
You connect them with the line thing. I forgot what it was called.
Just a bond. How many did I just use up?
6.
So how many do I have left?
18.
Okay. Now what do I do?
And you put them around the fluorine. And then there's no left after you do that.
Yep. Okay. Am I done?
I can double bond.
Okay. Is this what you mean? This what you mean, guys? Come on, don't be shy.
Yes.
Thank you. All right. Let's do a little formal charge here. This one's going to be 0, trust me on it. You have, fluorine has 7 valence electrons. There are 6 lone pair electrons plus 1 bonding pair, so 2 over 2. 7 minus 6 plus 2 over 2. Both of these fluorines are going to be 0. Let's talk about this fluorine. Again, we have 7. How many lone pairs are on this fluorine? How many lone pair electrons are on
4.
this? Thank you. How many bonding electrons?
4.
So I get 7 minus 4 plus 4 over 2. That gives my fluorine a positive 1 charge. Let's deal with bromine or boron. Boron has 3 valence electrons. It has no lone pairs, but it has 8 bonding electrons divided by 2. So my bromine has a +1 charge.
It would be a -1, I think.
I'm sorry, you're right. This is a -1 charge. Thank you. My bad. So if we accept your drawing of this for BF3, we have to accept that when fluorine is next to a boron atom, that the boron atom is going to grab an electron away from the fluorine. That will never, ever happen. It can't be. Boron will never, ever grab an electron from fluorine. So that means this does not exist. Cannot exist. But Mr. Popovich, that means that boron only has 6 electrons around it. Yes, ladies and gentlemen, that is true. An atom can have less than 8 electrons around it. It is possible. To be honest with you, I can't tell you of any other example other than possibly BCl3 or BR3. I don't think there are any others other than that. But
So
it is
what about
possible.
iodine?
Could be, maybe iodine's in there too.
Okay, basically like the halogens.
I believe, again, don't quote me on it, but I think those are the only instances in my knowledge where an atom has less than 8 electrons around it.
Would it, for example, like aluminum and chlorine together is what you're saying?
Aluminum and chlorine is an ionic compound. Understand, when we're doing Lewis dot structures, we are dealing with covalent compounds. We are not dealing with any ionic compounds. Okay?
Okay.
Does this make sense to you guys?
Question.
I'm here.
Can you just explain the reason one more time why the one on the left isn't correct?
Because fluorine is the most electronegative atom in the world. You can never put it next to a boron. Boron, if anything, has metal tendencies. It's not going to want the extra electron. And you put that right next to fluorine, there is no way in the world that boron is going to grab an electron from fluorine to become a -1 charge. No way is it going to happen. Plus, they have done studies of BF3. They've done crystal studies of it. And when you have a double bond, you get a shortening of the bond length. That does not occur. That does not occur in it. You have normal bond lengths. So in actuality, this is the true structure for BF3. Okay. Are we good with this? Any more questions on this?
So you said fluorine is the most electronegative?
Absolutely. Absolutely it is, by far. You put fluorine next to oxygen, fluorine will grab the electrons away from oxygen, and oxygen is the second most electronegative. Are we understanding this? Do we have this down? because I'm going to rock your boat again. Let's draw this one, SCl4. What goes in the center?
S.
Draw it over here. S goes in the center. I got Cl. While I'm doing this, figure out how many valence electrons there are. How many does chlorine have?
28.
4 times 7 for 28.
And
And
then
sulfur?
6. So it's 34.
1 times 6
Yep.
for 34 for 6. Okay, let's draw it, guys. What do we do first?
Put the bond,
Bonds.
single bond to the sulfur.
I just used up 8 of them. That leaves me with 26 left. Where do they go?
The outside of the chlorine.
They're lone pairs on chlorine. Two, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I have 2 electrons left over. Where do they go?
This is like that situation where there's an extra 2 in the middle, right?
My rules say if I have any electrons left over after putting them on the terminal, they go into the center atom.
Are we gonna get points off if we don't draw like the surrounding atoms like tilted away?
Yes.
Okay.
If you do not put the lone pairs in, yes, you will
No.
get points off.
Not the lone pairs. I'm talking about like when you put the electrons in the center. Are we gonna get points off if we don't tilt the chlorines? Because it affects the shape of the. It goes to like a pyramid shape from like a.
Where do you want?
What I'm saying is-
Where would you like me to put the? Where do you want to put the? Other
Well,
than
it
tilting
changes-
it like that,
it
where do you want to
changes-
do?
It changes the geometry.
No, it doesn't.
The lone pair. I mean the pair in the middle.
Well, the lone pair that will change the geometry when we get into Vesper.
I'm-
Absolutely, it will.
Right, and so in the Lewis structure, do we not draw it tilted?
They're
How would you want to
different.
draw it other than being tilted?
Like, yeah, exactly. You'd have to tilt it because
Okay.
they're pushing away from the pair. Like here, it kind of looks like the pair's on this. I don't know. Like if we're not gonna get points off, I don't really care. It's fine.
I'll tell you what, when we're in face to face again, draw it for me and I'll see if I accept it, okay?
Okay.
All right, guys, look. Count the electrons around the sulfur. 2, 4, 6, 8, 10. There are more than 8 electrons around the sulfur. You can do this. You can do it if you are in the 3rd shell and below. Look where sulfur is in the periodic table. It's in the 3rd level. Think. Do we have d electrons in the 3rd shell? Do we have
No.
d orbitals in the 3rd shell?
No.
We don't.
Yes, don't we?
Oh.
It goes
yeah, we
3p, 4s, 3d. So because sulfur is in the third level, it can access 3D orbitals to accommodate more electrons. Do you see that you can't do that if you're oxygen? Because there is no 2D orbital. If you are in the third level and below, you can utilize the d orbitals to stuff extra electrons in. Does this make sense to you?
So you mean like going down on the periodic table? So
Correct.
third shell, fourth shell, fifth shell.
All right, hydrogen's the first level. Lithium is the second shell. Sodium is the third shell. Now, if you look over from sodium over to where it goes aluminum through argon, anything from that level down, you can add extra electrons into the d orbital. That's where they are going. Any questions here? I got about 10 minutes.
I can say that I like I can follow the rule, but I don't necessarily understand where they're going in the d orbital.
Don't worry about it.
Okay.
Don't worry about it. We're going to take care of that. We're going to take care of that when we deal with something called hybridization. Okay? That is another topic that is literally, I have to go through. We're going to get through Lewis dot structures today. We're going to get on Tuesday, we're going to get through Vesper, and we are going to get through hybridization. Okay? I'm sorry?
Could we go over the problem on the homework that didn't make any sense because like the way I wanted it balanced?
Is this Chris?
Yeah.
Chris, we can go over it. You and I can go over it after I'm done doing this stuff.
Oh, okay. I'm sorry.
No problem. I'll be happy to stick around for a couple minutes. Yes, the noble gases will react. And yes, they do make compounds. So Jeremiah, how many valence, or where am I going to, what's going to be the least electronegative?
The least electronegative would be, where is XE? Oh, it's over there. And F is up there. So XE would be the least.
So I'm going to put XE. I'm going to put my fluorines around it. How many, since you already have the periodic table out, Jeremiah, how many valence electrons does XE have?
XE has 8.
Oh, we're dealing with 8 plus, how many does fluorine have?
Fluorine has 7.
8 plus 4 times 7. That's 28. I have a total of 36 valence electrons. Angelica, where do we put the first electrons in this compound? Angelina.
You're all right. You put it around XE.
Make the bonds between XE and each one of the F's. Subtract the 8 out. I have 28 left. Now, Angelica, where do they go?
You put them around F.
This is another reason why I like lines. It's easier to draw than dots. 2, 4, 6, 8, 10, 12, 14, 16, 18. 24. I have 4 left, Angelica. Where do they go?
You put them around XE.
Done.
Does it matter where exactly you put it around XE or no?
You mean, could I put them here and here?
Does it
Yeah.
matter at all?
You can put them here and here.
Okay.
You just have to have them exclusively on XE, and it can't be interpreted that they belong on the F. Does that make sense, Grace?
Yes.
Or it can't be interpreted they're a double bond.
Okay.
Okay, I got 5 more minutes. I'm intending to draw Lewis dot structures until I am, let me go through. I'm doing this off screen, so I want to make sure that already talked about that. Already talked about that. Sorry. Okay, I've done everything except resonance. Somebody remind me to talk about resonance.
Remember to talk about resonance.
Next week. You're very helpful.
I know.
Wait, didn't we talk about that already though?
We did a little bit. Okay.
Just in that, what did that mean? Never mind.
I do have a question though.
I have an answer.
How do you know when double bonds happen?
Okay, remember we didn't have enough around the center atom. If you don't have enough
okay.
around the center atom, you grab them from the terminal atoms to make double bonds.
That makes sense. Thank you.
Okay. Let's see. Who haven't I bothered recently? Kyle. And he's run out of the picture on me. Okay, what is the least electronegative atom? I3 minus.
Oh, out of I3 minus?
Yes. What's the least electronegative?
I.
Thank you. Good guess. So I'm going to put an I, and an I. Now, how many valence electrons?
21.
7. Or, yeah.
7. 3
sometimes
times
3.
7. That gives me 21. I have to account for negative charges. So what do I have
22.
here? I have 22.
Yeah.
Good. Now, Kyle.
Mhm.
Where do they go?
And you got to make the bonds first. So 2 lines there. Now you have what, 18. And then we're gonna go around the outside first. So the left one and the right one is probably where I'd start. So yeah, there.
All right, 1, 2, 3,
then,
12. Okay.
yeah.
How many do I have left?
Oh man. 6.
Where do they go?
All right. So I would start with I want to say you put it on the center, so the middle eye. But the issue.
Put them in the center.
Okay. Yeah, put
What
them in
was
the
your
center.
issue? What was your issue?
We're gonna have 2 left.
No, you don't.
Well, okay.
2, 4, 6.
Yeah.
You've used them up.
Yeah, but there's more than 8. I mean, does the eye by itself break the octet
Where's
rule?
I at? Is it below the third? Is it below the third shell cow?
I see you. Okay.
Can
it is.
Can the eye use some 5D orbitals? Is it below the third shell?
Yeah.
So it can employ d orbitals. Yes, you can put extra ones around the eye.
Gotcha.
Anything below that sulfur level. Anything below that. On that, I was like, anything on sulfur's level or below, you can add extra electrons around the center atom. Now, one more thing. This has a charge on it. To display this properly, you have to put the whole compound in brackets. And put the negative charge outside. To properly do a ion. That's what you have to do. Questions, guys? We're about at 8 o'clock. I'll probably start real quick. On Monday with a couple more examples of this. You are going to get a lot of work with the Vesper lab, because in order to do Vesper determination, you need to draw a Lewis dot structure. Are we good, guys? Is this making sense a little bit? I'm sorry, go ahead.
Your last statement there about the Vesper lab, that's just for the people that have you for a lab?
No, you guys are going to have, everybody has the Vesper lab.
Okay.
Everybody is in laboratory, has the Vesper lab. It is very, very good practice. You are going to have to do 18 compounds. And there are 5 questions on each compound. So you're going to have 90 questions for that. Yeah, I understand. But it's going to be work that's going to do you good. It's kind of like enforced homework. If that's all, guys, that's all I have to offer for right now. We'll be back face to face on Monday. Anything else, ladies and gentlemen?
Is the homework that's due Monday regarding Vesper or whatever?
The homework that is due on Monday?
Yeah.
Okay, I'm going to have to get out of here. I'm going to have to clear because I don't know what you're talking about.
Like the Pearson homework.
Yeah, I know you're talking about the Pearson homework. I just don't know what you're talking about with. Are you seeing the screen?
Yeah.
You're not seeing the screen anymore, are you?
Wait, hold on. I'll look it up on Pearson.
Okay, I'm here.
Not.
Oh, actually, I can do it here. You should only have 2 more homeworks left.
Yeah, but would our homework be on the stuff that we haven't learned yet? Like, could we push it back to due before Wednesday, and then whatever's Wednesday, do that Monday before the test, or no? I mean, what do you guys think? I just think it'd be easier to do the homework after you like learned it.
I got 3 assignments left.
Hmm.
I'm saying 3 assignments left, 10, 11, and 12. Am I correct in that, ladies and gentlemen?
10 was due today.
Yeah, you had us do what we just learned today this weekend. So now, like I'm a bad person. I did half of it, got stumped, and waited for the lesson today to finish it.
Okay. Fair enough. Fair enough. You guys need to yell at me. You guys don't yell at me nearly as much as my HCC class does.
Was that
What am I
good?
doing? That's not good.
Oh, sorry. I'll try harder next time.
Yeah, right. Oh, there it is. I got to see what I did to you. I will freely admit the Pearson homework for this particular area sucks.
Well, we could change that.
Not unless you're willing to grade all the homework for me.
Wait, are we extending the homework date?
We're talking about it.
Yeah, if you were paying attention, Chris, you would know that.
I think
I'm
we should
really
extend all the
sorry,
homework.
Grace. I'll do better.
Okay. I got to see what these questions are. This has got to go. Thank you. Okay. That was due today. I thought it was due July 12th.
Well, this makes me feel a lot better.
No, I'm sorry. I thought it was due July 12th. Where's home? All assignments. That was a mistake on my part. I am sorry.
It's okay. No one emailed you, so like you didn't know.
Assignment 11, I have due on the
The 14th, right? Because we would learn it next Monday.
You want to do it the 14th? I just gave you the 19th.
Oh, I mean, I don't care. Whatever. It's up to you.
And this one. Chapter 12, I believe. Okay, cancel, save. Yes. Okay, I moved assignment 11 to the 19th, 10th to the 12th.
Okay. Thank you so much.
No, I screwed up.
Yeah, that
you
would
have
make a big difference.
Well, I tried not to assign you homework before I discussed it at least. And I'm sorry, I'm just looking here. I'm trying to see. I believe chapter 12 is the chapter that we're not going to get to. Okay. Yeah, we're not going to get to that. So I got to figure out how to take it out. Okay. Don't worry about it. You won't be held responsible for chapter 12.
Okay.
Thank you for telling me. Who was that?
Grace, per usual, because I'm.
Okay.
It was Chris.
That was Grace Serini, not Chris.
I thought it was Chris. I don't know.
Was it Chris Serini?
Yeah, it was Chris Corsa.
Yeah, I
Chris
heard
Serini,
I
Chris
heard
right?
Chris, but I
Actually,
don't
my
know.
dad's name,
Yeah.
so that's really weird. My dad's name's Chris Serini, so.
Okay. Chris
Can you
gets a
tell
point.
us-
Chris gets a point.
All right.
Grace gets a point.
Okay.
Okay. Chris had one from earlier. Okay. Anything else, guys? Don't worry about chapter 12 will not be counted for sure. Do not do it. I don't think I'll get to any part of chapter 12.
Are you able to tell us what day test number 3 is?
I told you that it's the 19th.
Okay, thank you.
Test 3 is the 19th. The final is the 21st. Okay? Maggie?
Yes, thank you. The 19th is going to be a horrible day.
Why is that?
All of my tests are on the 19th.
I feel you.
Is that that's the lab
3 of
day
them.
too, isn't it?
Yeah, I have
That's the lab final.
a lab final for biology final, and your test. It's gonna be
Yeah.
It's
My
all right, you
test
can
is
do
going to,
this.
well, think about it. I've only got three lectures, Maggie. How hard could my test be?
well, since we get our notes. I'm happy about that.
I know Chris needs something to talk to me about. Anybody need anything to
No,
talk about?
It's fine because the homework was extended, so I'll just get it right next time.
Okay, well, you know you get extra, you get more than one opportunity, Chris.
Yeah.
Okay, did you need that question talked about? Which one?
No, it's fine. Like it's all
Well,
good.
talk to me. Which one was it?
It was question. I don't know what number. So.
Okay.
Yeah. It was a question. It's fine.
Okay. Guys, are you pretty solid on what we went through today?
Yeah.
Pretty
Yeah.
solid?
Yes.
Okay. That's fine as kind. I'm happy to hear that. You have questions, please, I'm available, all right?
I have a question real quick.
Yeah, Carly.
So I know you said that if you said 90 or higher on the first 3 tests, we don't have to take the final.
Didn't I announce who? I thought I gave an email as to who was still eligible.
Oh, I meant to ask if it was like with the
It
extra
is.
credit.
No,
It
it's
is?
before extra credit.
Okay, gotcha.
Carly, you're eligible yet. Carly, you're still eligible.
Okay, yeah, thanks. I was just seeing how good I had to do on the next test.
Maggie's eligible yet.
Did you squeeze in like 3 points for me on the first test?
No.
Damn. Oh, I was so close.
Yeah.
Maybe I'll just look it over again and find something else to argue with you about.
Too late.
Damn.
Or there's this nice little line in the syllabus that says that you have 1 week to dispute grades.
Define a week.
Define a week.
Yeah, I don't know the legal definition of that. So
7 days.
what's a day? Are we using Gregorian days?
168 hours.
I'll get back to you on that.
Ah.
All
Okay,
right.
guys.
Thank you.
If you don't need anything more, then I will see you later then, all
Okay.
right? See you on
Alright.
Monday.
Thank you.
Take
You
care.
have a good night.
You
You too.
too.
Thank you. Good night.
Thank you, Professor.
Take care, Jeremiah.
You as well.